Hello, welcome back to the second part of upstream downstream word problems. In the first part we discussed some variants of our upstream downstream model where a boat goes upstream, turns and goes the same distance back downstream. Remember the 5 quantities in such a problem: the speed of the boat in still water, b, the speed of the river, r, the distance d between starting point and turning point, the time tu for traveling upstream, and the time td for traveling downstream. Do you remember that the actual upstream speed is b minus r and the actual downstream speed is b plus r? Then, since rate equals distance over time, we have the following two equations. The upstream equation, b minus r equals d over tu, and the downstream equation, b plus r equals d over td. Typically, 3 of these quantities are given as constants, and the other 2 are the variables. But things get more interesting and more difficult if we have 3 unknowns, 3 variables. Of course, we also need one more equation, relating some of these variables. Often the 2 times are unknown, and some relation between them is given. An example is where both times are unknown, but the total time, the sum of upstream and downstream time, is given. So here's an example. A boat travels 15 miles upstream, turns and travels back to where it started. The total time for the journey is 3 hours and the speed of the river is 2 miles per hour. What is the speed of the boat in still water? We plug the 2 known values, distance equals 15 and river speed equals 2, into the upstream and downstream equation above and get b minus 2 equals 15 over tu and b plus 2 equals 15 over td. In addition, we have the third equation, tu plus td equals 3. So 3 equations and 3 variables, b, tu, td. We solve the third equation for tu and get tu equals 3 minus td. Plugging this into the first 2 equations gives b minus 2 equals 15 over 3 minus td, and the other one unchanged, b plus 2 equals 15 over td. Then we solve the first equation for b as b equals 15 over 3 minus td plus 2, and replace b in the second equation by this expression to get the rational equation in one variable, 15 over 3 minus td plus 2 equals 15 over td. We simplify the 2 plus 2 as 4 and multiply the equation by the LCD, which is 3 minus td in parentheses times td, to get 15 td plus 4 times 3 minus td in parentheses times td equals 15 times 3 minus td in parentheses. Or if you distribute 15 td plus 12 td minus 4 td squared equals 45 minus 15 td, or collecting like terms, 0 equals 4 td squared minus 42 td plus 45. So we have a quadratic equation. Using quadratic formula we get td equals 42 plus minus square root of, well, negative 42 squared minus 4 times 45, all divided by 2 times 4. So we get 42 plus minus square root of 1044 divided by 8, which is 42 plus minus 32.3 over 8, about 9.3 or about 1.21. What about td equals 9.3? We need 9 hours to go downstream when the total time is 3 hours. That means that the upstream time would be negative. It is obviously nonsense. It makes sense in the math but not in real life, since we get a negative time. Note that you are supposed to recognize if something like this pops up from the math. Always check with common sense. So let's now check the second solution, td equals 1.21. Plugging this into the equation b equals 15 over 3 minus td plus 2, we get b about 15 over 3 minus 1.21 plus 2, which is 15 over 1.79 plus 2, which is about 10.4. Then the actual upstream and downstream speeds are about 10.4 minus 2, which is 8.4 miles per hour, and 10.4 plus 2, which is 12.4 miles per hour. The time for going upstream would be about 15 over 8.4, which is 1.79 hours. And for downstream, 15 over 12.4, which is about 1.21 hours. It checks. Other versions give another relation between the times, as in the second example. A boat travels 25 miles upstream, turns and travels back to where it started. It takes 1 hour longer to go upstream than to go downstream. If the speed of the boat in still water is 10 miles per hour, what is the river speed and what are the times? Well, upstream downstream equations, 10 minus r equals 25 over tu, and 10 plus r equals 25 over dt. Note that r is unknown now and b is given. And of course, the third equation, tu equals td plus 1 hour longer. Let us first eliminate r. We solve the first equation for r equals 10 minus 25 over tu, and plug into the second equation to get 10 plus 10 minus 25 over tu equals 25 over td, or 20 minus 25 over tu equals 25 over td. Then we multiply the equation by the LCD, which is tu td, and divide by 5 to get 4 tu td minus 5 td equals 5 tu. For all this, we didn't need or change the third equation expressing the relation between the times. So it is still there, and we have two equations in the two variables tu and td. Replacing tu by td plus 1 according to our time relation, we get 4 times td plus 1 in parentheses times td minus 5 td equals 5 times in parentheses td plus 1. We simplify the equation and get 4td squared minus 6td minus 5 equals 0, another quadratic equation. So we use quadratic formula again. Td equals 6 plus minus square root of 36 plus 80, all divided by 8, which is 6 plus minus square root of 116 divided by 8, which is approximately 2.1 or 0.6. Then tu is 1 more, so 3.1 or 1.6. For the river speed, we use r equals 10 minus 25 over tu and get either r equals 10 minus 25 over 3.1, which is about 1.9, or r about 10 minus 25 over 1.6, which is about negative 5.625. This is impossible again, so we have only one solution, r about 1.9. What if upstream doesn't take 1 hour longer, but say 50% longer than downstream? Instead of the difference of the times given, the quotient of both times is given, 1.5 in our case. So, example 3. A boat travels 25 miles upstream, turns and travels back to where it started. It takes 50% longer to go upstream than to go downstream. If the speed of the boat in still water is 10 miles per hour, what is the river speed and what are the times? Well, the upstream-downstream equation again, 10 minus r equals 25 over du, and 10 plus r equals 25 over td, exactly the same as before. And the equation between the times, tu equals 1.5 times td. 50% more means multiplying by 1.5. Since the first two equations are exactly the same as in example 2, they can also be reformulated into one equation in the two variables exactly as they are. So we get 4 tu td minus 5 td equals 5 tu, exactly as before. But now we substitute tu by 1.5 td from the third equation, and we get 6 td squared minus 5 td equals 7.5 td, or 6 td squared minus 12.5 td equals 0. Again a quadratic equation, but a simpler one, which can be solved without quadratic formula, just by factoring. We factor td and get td times, in parentheses, 6td minus 12.5 equals 0. So by the zero property, either td equals 0 or 6td minus 12.5 equals 0, meaning td equals 12.5 over 6, which is about 2.1. Then tu equals 3.1. By the way, td equals 0 is obviously impossible, so we have just one solution here again. For the river speed we get r equals 10 minus 25 over tu, which is about 10 minus 25 over 3.1, which is about 1.9. It's almost the same solution than in the previous example, since of course the times are about 1 hour apart. But this is a coincidence. So what is the conclusion? We looked at more difficult versions of the upstream downstream problem with 3 variables and 1 additional equation in addition to the upstream and downstream equation. Using substitution method we could reduce the system to 1 equation in 1 variable, but the equation was also more difficult, a quadratic one, than in the basic versions. Thanks for listening.